Alright, in this mini lecture we're going to pick up from where we left off in the previous mini lecture, diving into a little bit more detail on the thermodynamics of this chapter, and then getting into our first quote-unquote real reaction. So thermodynamics is really answering the question of what's favorable and what's not. So what we know about the general mechanism for chapter 20 and actually 21 is that for these carboxylic acid derivatives, they have a leaving group attached to the carbonyl carbon, and so when a nucleophile attacks, and it could be negatively charged or it could be neutral, I'm using a negatively charged one in this example, we invariably get a tetrahedral intermediate. The tetrahedral intermediate then collapses to give me a new carboxylic acid derivative plus my leaving group. And it doesn't take a rocket scientist to see that these are all potentially, so it's nucleophile. Well, you know, we've answered this kind of question before. It's all about equilibrium and where the most favorable products, what the most favorable products are. It's all about stability. So for example, back in the acid-base chapter, when we would take Cl- to remove a proton from this proton donor, acid, base, conjugate base, we would compare this base to this base and see that Cl- being much weaker and more stable than N-. Similarly, when we looked at the SN2 reaction, we could draw a mechanism that kind of looks good. I can kick out this leaving group to make this substitution product. But again, looking at the stability of Cl- versus O-, that's much more stable. So again, the equilibrium lies to the left. This is not a favorable reaction. Well, it's exactly the same thing in chapter 20. When I have Cl- here reacting to give me up, down, and out, kicking out OCH3, and the whole up, down, and out is our cheater's way of showing the mechanism. Don't do that when I ask you to show the complete stepwise mechanism, please. But it's good for predicting the products. So here is a reaction where Cl- adds to my ester, kicks out OCH3-, and now I compare this to this, and of course the Cl- yet again is the most stable. So our equilibrium constant, which is, you know what? Cl-. Alright, so this is all summarized very nicely in what we call the reactivity ladder. It's all about comparing the stabilities of these carboxylic acid derivatives. When you think about the leaving groups that are being kicked out, it's really evident based on pulling everything together that we've learned over the course of this OChem 1 and OChem 2 that, boy, these leaving groups up at the top are nice and weak and really stable. So they're happy to get kicked out, and that means this is going to be the most reactive carboxylic acid derivative. In fact, acid chlorides and acid anhydrides are both very reactive. If you open up a bottle of an acid chloride, you'll see a lot of fuming from reaction of that acid chloride with moisture in the air. The fuming on an ester is none. So what this boils down to is, if I want to make an acid chloride from an amide, for example, by doing, let's do this. and do our little up, down, out, up, down, and out to give me this plus that, that is not going to be favorable because the nitrogen is going to very happily come back and kick out the chloride in a heartbeat. Well, that obviously poses some issues. Later.